again, great fortune of having somebody who's trained diffusion models. So he was the Chitwan is here, and he was again at Google before, and he was one of the first authors, I believe, of the Imagine paper, which does image generation. So Chitwan will talk to us today about diffusion models. Um, so Chitwan, please take it away.
Okay, perfect. Okay, so hi everyone, I'm Chitwan. And right now I'm working at Ideogram AI. I've been working here for two and a half years now. And before that, I was at Google. And over the last maybe 3 years, I've been working on diffusion models. And yeah, it's great to get a chance to talk about these models. I've been personally just been very, very excited about working on this. And I'd love to share about some of the details and introduce you to this new class of generative models in an hour, which is a very hard task, I realized when doing these slides, but hopefully I'll do a good job at it. Okay, so before we start discussing about diffusion models, let's set the goal straight. So what we are interested in generally is that, let's say we have a large corpus of images and we want to train a generative model. And what we're interested in is basically sampling new images from this model. So I'm sure you have learned about LLMs in your previous talks, and there the goal is to model text. And here we are specifically interested in modeling images. Images is just one instance where diffusion models are used for, but that's what popularized diffusion models the most. And now diffusion models are used for generating videos or generating audio and many other things. But for the purpose of this lecture, we will try to focus on images for simplicity, and all the ideas that we talk about are going to generalize to other domains as well. And before we talk about diffusion models, maybe one thing we should try to think about is why can't we use an autoregressive model to generate images? Because if we can use autoregressive models for generating images, then there is not really a need to introduce a new class of generative models just for modeling images, for instance. So I'll just give you like a quick overview of how you could go about generating images with autoregressive model and what are the main pitfalls that you see in this process. So just as a quick introduction, in autoregressive model,
Chitwan?
yeah, go ahead.
Yeah, just a quick clarification question. So in the goal there is no objective on conditioning on something. Like for example, in images, like we do want a controlled image generation, that given a text, you want an image. So
yes,
but
yeah. So generally, we have. So I'll eventually try to generalize to a conditional image generation, but you can also just apply this thing for unconditional image generation. So you can just assume right now that conditioning is just empty. So there's no conditioning. So every time I generate an image, I just get like a random image, but that just still looks like an image basically. And eventually we will see how do we adapt this to text to image or text to video or like or any kind of condition signal. It's actually like a very straightforward addition eventually to these diffusion models. So basically in autoregressive model, I'm sure you already know this, but I'll just give you like a brief primer here. When we have a sequence of tokens, the way we formulate an autoregressive model is through this causal factorization. And this factorization basically allows us to compute exact log likelihood and allows us to just maximize this log likelihood efficiently using modern transformers. And this is the crux behind the modern language models that are used to model text. Now, one of the main disadvantages of autoregressive model is that in order to compute this tractable log likelihood, you have to add this constraint to the model where it has to have this causal structure where a token can only depend on the tokens before it and cannot depend on the tokens after it. And another disadvantage of autoregressive models is that during generation, it's a very slow process because you can only generate one token at a time. And that also just happens to be the case because of this causal masking that we apply. Now, let's see how we can do image generation using autoregressive models. So let's consider like an image that we have here on the left. And this is a 1680 by 1122 by 3 matrix where each value is in 0 to 255. So it's like a discrete tensor, three-dimensional discrete tensor, and we want to model it somehow. So for autoregressive modeling, what we will do is that we will basically flatten it out into a sequence of tokens, and the vocabulary size would be 256. If we flatten this image out naively, we would end up with 5.65 million tokens, which is extremely long sequence length for modern LLMs to deal with. So you can already start seeing what kind of problem that can happen with this kind of method, where we naively just tokenize each pixel as a separate token and model using autoregressive models. And it has been tried before, so I would recommend you to read generative pre-training from Pixels, where they try it on like the 32 by 32 images, and even there they say how challenging it can be to model images like this. So one thing that most people who try to model images using autoregressive model do is that they try to somehow compress this image into a smaller latent space and train a transformer autoregressive model in that space. So imagine what we do is that we take this image of a dog, and each 16 by 16 by 3 patch of this dog, we map it to one of these discrete embeddings. So let's say we have a table of 32,000 embeddings, and we somehow learn this mapping that each patch is basically going to be mapped to one of the entries in this embedding. And the way we train this mapping is that there is an encoder and there is a decoder. The encoder basically learns this mapping. And then the job of the decoder is to take this mapping and somehow reconstruct the image back. So this is basically like an autoencoder model where we are just learning this kind of mapping. And once we have this mapping, we can basically train a transformer model on it using autoregressive modeling. And during inference, we just generate these tokens and then feed it back to the decoder, and that will generate the final image for us. So just applying this idea back to the original image, we can see that if we have a 16 by 16 by 3 patch mapped to a single token, we reduce our 5.65 million token sequence to a 7,000 length sequence, which is much more tractable compared to what we were dealing with before. And this approach has been shown to be very promising, and a lot of papers have actually applied this approach to a lot of success. And this is primarily the main method by which people use autoregressive models for image generation right now. And yeah, I've just linked some of the papers that try to scale this approach, and they have shown a lot of success as well. Now, what is the main limitation of this approach? So the main limitation, as you could have guessed, is this mapping that I talked about initially. So if you just consider what kind of compression we are dealing with here, so a 16 by 16 by 3 patch where each value is a 8-bit value. So this is basically a total of 768 bits that are being mapped to 15 bits, which is 32,000 tokens that we are trying to map it into. So this is like an extreme amount of compression. And generally what we end up finding is that this compression leads to imperfect reconstruction of images. And this encoding is an upper bound on how good our generative model can be, because even a perfect autoregressive model can only do a perfect mapping in this constrained latent space, and the decoder eventually, when it will reconstruct the image, it will just do a bad job at it. And here I've shown you an example of like a parrot image and the reconstruction performance of different autoencoders that people have tried in the industry. And you can see that in each of these reconstructions, there is something that is being lost. Sometimes the images are blurry, sometimes the images are missing crucial details. And this is one of the reasons why there has been this disadvantage with this modeling approach, and why people have started working on diffusion models for image generation. Also, another disadvantage that I haven't mentioned here is this order of image generation, where you generate the top left patch first, and then you go from left to right and top to bottom to generate the entire image, which may work very well for text, but it's not as intuitive why an image should be generated like that. So for instance, let's say I want to generate an image where I know what the eye of the dog looks like, which is here, but there is no way for me to condition the first patch prediction on this because of the causal structure. I just am constrained to generate the image from left to right and top to bottom. So yeah, do you have any questions at this point regarding autoregressive model?
Yeah, so question, Chitwan. So
yeah,
I mean, I guess if you are, I'm just thinking out aloud, by the way, right now. So, I mean, you're talking about generating the image in an autoregressive manner from, left to right and so on. But what if I use like some, uh, how do I say, successive coarser and coarser approximations of the image. And then I say that, hey, actually, I will generate the coarsest one first, and then I will generate the next coarsest one, and so on. And maybe there'll be some tokens over there, but uh, and maybe it is starting to come back to a diffusion-like process. But is that something that one can try to do with transformers?
Yeah, that's actually a great question. And I think one of the recent papers that have tried to do it is fractal generated models.
Okay.
So they basically try to break an image into fractals, and yeah, you exactly how you described it. They first generate like a coarse version of the image, and then so you can imagine that you have a small transformer that would do the generation part of that 16 by 16 pixel on its own, while there is another transformer that generates each patch at a time. And you can further divide that task up by into different transformers of different sizes, and that's how you could generate an image from coarse to fine grain. And I think ChatGPT 4.0 might be using an approach like that for image generation as well.
Oh, the Ghibli one, is it?
Yes, yes.
Let me see. Okay.
Yeah, so before I start talking about score matching and diffusion models, I just wanted to emphasize how impactful these models have been. And these models have been adopted and have been a state of the art so far on image generation, video generation, and even people have tried it for text generation now, and it's looking promising. And also any kind of continuous data. So even protein generation, people are using diffusion models for, or any kind of continuous data that you can imagine. So text would be a discrete data, but most of the other data that we generally deal with has some continuous form of it. And diffusion models have just been a method that you can just slap on top for any of this data modeling, and it just always reliably works very well. So this class of models has been really promising, and it has only been 5 years since these models have been around, and there has been so much impact that these models have delivered. Okay, so let's first talk about score-based generative models. So one confusing thing that might be here is that I always talk about score matching and diffusion models. And these two are actually very different lines of research that were done by different groups of people. But eventually, these two methods agree on the exact same objective function, even though they arrive at it with a completely different line of reasoning. And I will try to emphasize that connection as a part of this talk as well. So first, I'm going to talk about score models. And the first question you may ask is, what is actually a score? And the way you can define score, the way the score is generally defined here is basically given a random variable x, which has a certain probability distribution, p of x. The score is basically the gradient of that log likelihood with respect to x itself. And one thing that may be very obvious here is that this x must be continuous random variable here, otherwise the score is hard to define. And I mentioned earlier that image is basically like a discrete tensor, but you can basically make it continuous for the purpose of score modeling and diffusion models. And so for example, we describe images as a number between 0 to 255, which are the pixel values. But you can normalize it between 0 and 1, and you can treat it as a continuous variable. And the reason it works is because even though we represent images as these discrete numbers, there is nothing discrete about them from the data perspective, because you can say this for text where a token 5 can be very different from token 6, and a token 5 can be very similar to token 10,000. But that's not the case with images. The pixel value 5 is actually very close to pixel value 6 and very far away from pixel value 250. So making them continuous actually works fine, and that's something that we need for score modeling. The core idea of score models is that given a set of data points from the distribution P of X, so let's say given images from this distribution of images, we train a neural network to learn the score function. And once we have the score function, we can use this to generate new samples from the model using Langevin dynamics. So I'll just give you like a brief overview of what Langevin dynamics is and how we can use the score function to generate samples once we have access to like this score learned from the distribution. So, yeah.
Just before we go there, is there a intuitive definition of what the score represents? I know, like
Yes.
uh, like why is
Yes.
this
So
log important over this, and why exactly the gradient?
yeah, so I'll actually give you like an introduction here in this
Okay,
Langevin dynamics slide
okay,
here. So Langevin dynamics basically is like this iterative process where we start from an X that can be sampled from a distribution that we know how to sample from. So let's say like a standard normal Gaussian distribution, we just sample like a noise matrix, and we apply this iterative update process to that image. And over time, this process guarantees that the sample that we will converge to would be a sample from the actual P of X distribution that we care about. Now, why does that happen? So one intuitive way I can tell you that why this can happen is that this can be looked at as a gradient ascent algorithm, where every step we are taking a small step in the direction of a region which has higher log likelihood under P of X than we were at before, right? Because this is the gradient update that we are applying to X at every sampling step. And if we keep applying this for long enough time and our step sizes are small, we would converge to a sample from the probability distribution. Does that make sense?
yes, it does. And then I'm just thinking, like, are you? I mean, is the other intuitions, for example, like if my score function is convex, am I always guaranteed to reach the same point as because
Yes,
in
that's
gradient
actually a
descent
very
as
good question. Yeah, so this is why we also have this noise vector as an input at every step. So you see that we add a small amount of noise to this sampling process, and this is basically what gives us stochasticity in this entire sampling process. So the stochasticity that we're obtaining is coming from the original input that we get, and also this random noise that we are adding to the sampling step at each step basically. And I'm not going into too much detail into like how like I'm giving a very hand wavy argument regarding this right now, but there is a whole derivation of like how we arrive at this update process and how we can prove that this would actually converge to a sample from P of X. But this basically shows you that if we have access to this score function somehow, then we can apply, like we can substitute it here and actually start obtaining new samples from the probability distribution that we actually care about.
And just to again, like, what are the properties that P of X must satisfy so that this Langevin dynamics actually converges to that? Do you like? I know Nilesh said something about uh, being convex or so. Is there anything?
So that's actually a good question. I don't remember it on top of my head,
Okay.
but I do remember that. So Langevin dynamics is actually not something that is only used for score matching. It's actually
Yeah.
like something that has been used for all kinds of like it's a go-to process for sampling from any energy-based models basically, and approximating the normalization constant of energy-based models. So I think they are actually very general for the probability distributions. Now, I guess the probability distribution should be continuous here for this to work, but there are also probably some discrete generalizations to this as well. But I'm not exactly sure what are the properties that probability distribution need to
Yeah. And I'm guessing that
satisfy.
there is
Yeah.
something special about images, right? Which kind of makes it work even better, or like even
Actually,
audio.
I don't think so. I think it works equally well for audio, video, and everything. So
Okay.
I think yeah, it's fairly general from that perspective, I think.
By the way,
Okay, so yeah.
sorry, Nilesh and I are asking questions, but the rest of the class, and mainly we are asking questions so that the rest of the class can also follow it in a more gentle way. But everybody else should feel free to interrupt the speaker if they want clarifications. Huh? Go ahead.
Yeah, so now that we know that if we have access to score function, how could we obtain samples from it? The main question is that how do we learn this score function in the first place? So essentially, if we just write out the objective function that we care about, this would what the objective function would look like, where let's say we have access to this ground truth score, and we feed this input to the model, and we just optimize this regression loss and approximate this objective function using the data samples that we have from the probability distribution already. So this looks very much like what we generally do for maximum likelihood estimation. Here, our targets are just different, and we're just trying to learn this regression function to approximate the score. But there are very clear problems here. And the first obvious problem is, how do you get access to these ground truth scores? We don't have these ground truth scores with us. All we have is data samples from this probability distribution. So we somehow need to figure out how to obtain this. And also the second very interesting subtle problem that happens with this is the fact that there is this probability weighting on this objective function. So this means that we are only learning score for data points which already have very high likelihood under the data distribution. So anything beyond that, we are never learning score function for that, and the score function that we will learn will more or less be random at those points. Now, why do we care about learning score function at those points? So let's just consider this update rule again that I showed in the previous slide. So let's say now we start from an x0, which is a sample from standard normal Gaussian distribution, and I start applying these updates. So one thing that would be true is that if P of x is a distribution of natural images, then the probability of this x naught under that distribution would be essentially 0. And so we would never have learned a score function for that kind of data, and our score function will essentially be random. So we would not really be making any progress towards the data distribution in this process when we start out. And if we do not take steps in the right direction towards data, then we would never arrive at a point where score function is actually meaningful, and we would just like keep going around in this large dimensional space without making any progress. Now, how do we solve this problem? And one way to solve this problem is that we construct new distributions based on this data distribution. So imagine that we define a distribution P sigma I x, where what we do is that we take all these data points, we add some Gaussian noise to them, and now we induce this new distribution marginalized over data distribution, which is, so you can intuitively think of it as a data manifold distribution, and then you add slight bit of noise to it, and you expand the support of that distribution a little bit. And it's obvious here that the higher the value of sigma, the higher the support of that distribution will be. And if you choose sigma to be very high compared to the actual magnitude of the values of x, then you would basically cover the entire, it would basically become a normal distribution at that point, because you can ignore the mean there. And that's basically how we can slowly expand our original data distribution into these peripheries of distribution, basically. And the way we define it is that our initial sigma 0 is the smallest sigma, and that's essentially very close to 0. So this means that P sigma 0x is essentially the same as P of x, and we keep increasing the sigma as we go, and the sigma n would be the largest sigma, and it would be so high that is essentially a Gaussian distribution at that point, and it has no connection to the data distribution that it came from. So this is basically, first of all, we define these distributions. And then we learn score function for all of these distributions. So if you remember the previous objective function, we basically modified it by adding a summation term here, where we are not only learning score function for the first distribution, we are learning it for all the n distributions. And we have accordingly weighted, we accordingly have the expectation of those distributions here. Now, one more change that we have made here is that we are sharing the parameters of the score function across all these distributions. So instead of just providing x as an input to the score model, we are also providing the sigma I as a proxy to what is the distribution for which we are modeling the score function right now. So that's why this is, in the original paper, they called it noise condition score network. because we are basically sharing the parameters across all noise levels. Technically, you can learn different score models for different noise levels, and that is maybe how you scale the size of these models, but generally we just share the parameters. And here lambda I is the weight, loss weight. So basically it allows us to weigh different distributions in different ways, maybe learning score for some distributions easier than other distributions, and we can decide the weights later on. So I'll get back to this eventually, how do we decide the weights. There's also still one problem that we haven't really solved here, and that problem is that we still don't have access to these ground truth scores, right? And we somehow need to compute them. So here again, I would make one very big leap, and I would really encourage you all to like read this paper from 2011, where there was this beautiful result that this quantity here is exactly the same as this quantity here, in the sense that if you train the model on these two objective functions, you end up learning the same score function. And the interesting thing here is that the first quantity is intractable while the second quantity is fully tractable. And I'll show you how we can exactly compute this score. Okay, so the way we defined P of x bar given x is basically like a Gaussian distribution. I'm using a C constant here because it doesn't matter eventually. And we take the log of it, we get this quantity, and now the gradient of this with respect to x bar would just become this quantity. And this is perfectly tractable. We have access to it, and we could just plug it in as a target, and we can start training the model for score estimation. And I can further simplify it. So x bar, to sample x bar from x, we would basically sample an epsilon, which is a random standard normal Gaussian noise vector, multiply it by the standard deviation, get this x bar, and the difference between them would basically be the noise itself divided by the standard deviation of the distribution. So just to put this thing back here, so we started out with this objective. The target now becomes just epsilon upon sigma I. And what I'm doing here is that I'm reparameterizing the score function to fold in sigma I and the negative sign here. So just to make the objective function a bit simpler. And the way I have decided the lambda I here is that, as you can see here, the epsilon is always a sample from standard normal Gaussian distribution. So it has a fixed norm. And for different levels of noise, the norm is basically being decided by this sigma I. So the larger the sigma I, the lower the norm of this loss function would be for that particular distribution, and so on. So in order to make the norm of the loss the same across different noise levels, we can basically select lambda I to be sigma I squared. And this is basically the recommendation from the original paper. And if we do that, then this denominator gets canceled out, and we get this very simple objective function that we need to optimize now. So just putting things back together in the form of a simple training algorithm. So we get a training data point x. We sample one of the noise levels, sigma I, and we sample a noise from the standard normal Gaussian distribution, and we basically optimize this objective function. So as you can see here, we are trying to learn the score, but essentially what we are training is a noise conditioned denoising model. So you take an input, you add some noise to it, you tell the network what is the variance of the noise you added, and you ask the network to denoise that image. And it turns out that this is basically the title of the original paper that I talked about, which says a connection between score matching and denoising autoencoders. And this is one of the most beautiful results that really excited me and made me work on score models. And any questions at this point?
Yeah, so can we just intuitively parse what this objective function is saying?
Yes. Yeah. So this
Uh,
objective function is basically saying that I get a data point. So let's say I have an image. I add and I first sample a variance of noise that I want to add to that image. And then I add that noise to the image. So now I get a noisy image, which is x plus epsilon sigma I. And I
which is
train,
the X bar that we were.
yeah, which is the x bar, exactly, which is the x bar. And I train the model to predict the amount of noise that I added. So essentially, I'm training the model to denoise the image, because if I know the amount of noise that I added, then I can subtract it back and get the original image back. So I'm feeding a noisy image to the model, and I'm asking it to denoise it.
I'm feeding a noisy image, and I'm also giving it how much the degree of noise I added.
Exactly.
And I'm trying to estimate what was the exact noise.
Yes, exactly.
Or the normalized noise that I had. Okay.
Exactly. So this can be reparameterized in many ways. You can also ask it to predict X instead of epsilon here, right? Because that's the only missing information that you have in order to denoise the image. Typically, we use this parameterization because here the target is very well normalized. So because images can have different norms, whereas epsilon will always have a predictable norm. So this is a much more stable loss function generally.
Okay. And in case like if we have a little bit of time, maybe like later, like I wanted to just go back and see like what was the leap of faith that we took, and like how do those expressions differ exactly. But yeah, I think like we are already short, so
yeah,
we should
it's
just go
actually
ahead.
also something I would recommend like reading that paper because it's
Okay.
actually like a very simple paper, and it's actually it's one of the I think the paper that I read and I was just like wow, and yeah.
Okay.
But at that point they actually didn't suggest to do any of this thing. They just showed this connection, and it's fascinating that 10 years later people dug that paper up and figured out how to and actually apply it to score matching and train generative
Yeah.
models.
And making Ghibli images now.
Yeah.
Probably.
Ghibli images may be coming from a different class of models though.
Yeah.
So
Could be.
yeah. So now if once we have trained this model, we can go back to that sampling algorithm and start sampling and everything would just work. And it actually does work. So for example, you can see these are some visualizations from the original paper, how the sampling trajectory looks like. So we go from the left to right here, and we initially just sample Gaussian noise and start applying these Langevin updates. And you can see that eventually what this actually looks like someone is just slowly denoising your image, right? So and that's basically what is being conveyed in the training objective function as well. So also just to emphasize here, this is like I think a 2020 paper, and at that point, even generating images of this level was considered like a breakthrough. So this is like a 32 by 32 image, and if you can generate like these faces like this was considered like an outstanding paper. And now, of course, we can see how stunning images we are able to generate in the span of like 3 to 4 years.
Sorry, so in this slide, you were just like training it with images of faces or so.
Yeah, so I think there are some data sets. I think there is a Celeb AHQ data set, which is just faces, which was used as a benchmark for generative models. And here you can, and these are all unconditional generations, so you don't provide any condition signal, you just generate random faces here.
And
I
in
think
this, sorry, go ahead. Yeah.
I was just saying that the bottom one, I think, is CFAR 10 data set.
I see. And I guess like how many X's do you need to have kind of even this kind of generation?
Yeah, so that's a good point actually, and I think this is one of the things that these models are most notorious in. And generally, you need like few hundreds to like even thousands of steps sometimes to generate samples, and each step is basically running a forward pass in the model, so it really gets expensive. And there has been a lot of research into figuring out how to make them faster. And there are different sampling algorithms that allow you to sample in like 4 steps or 8 steps without losing a lot of quality. And even 1 step nowadays you can sample from these diffusion models. So yeah, it's an active area of research where people are just trying to make these models as fast as possible. And I guess a lot of those papers are basically taking this sampling algorithm. And as you can see that given that it's kind of like a gradient descent algorithm, all the things that people have worked on optimization, such as momentum, Adam, and all these things also apply here. And people have been basically trying to figure out how can we create trajectories where we can take very large steps using the gradient that we predict. so that the step size, once the step size become large, you can take less number of them and arrive at the sample quicker.
And in this case, when you say step size, if you go back to that slide,
yeah, step size is the epsilon
the number
here.
of sigmas that you need to take.
So the number of sigma would be the step size here. I think so. In general, it's actually independent. So you can run this multiple times for each sigma as well. So you have that freedom too. So you can say that I want to converge to each of these distributions independently before moving on to the next distribution. The step size I mean here is this epsilon.
Sigma.
Yeah.
So have people tried some second order updates here? Like
Yeah,
using...
there are a lot of papers that have tried second order updates for this as well. Yeah.
And
I think
work
that's
well?
and that's, I think, the current best accepted way for fast sampling.
When you say that is, what do you mean with second order?
So there's this paper DPM solver that I have linked to at the end. And and that's like, I think, one of the most accepted papers so far for making faster samplers using second order optimizers. Okay, so this was basically score-based generative models. And I want to highlight here again that we never talked about maximizing log likelihood of data like we talk about in autoregressive model. We said that all we care about is sampling from this distribution, and all we need to sample from this distribution is to learn the score. And we basically learned a score model to model the score. So there is no reason that what we learned here should have any correlation with actually maximizing the log likelihood of the data. And this is basically where diffusion models come in, where this is a completely separate class of models that were actually trying to maximize log likelihood of data. And what they find is that they eventually arrive at the same objective function, which is basically the beauty of it all. So I'll now talk about a completely different class of models, and you will see how much similarity there is between them, even in the construction of diffusion models. But let me just get started in the interest of time. So in diffusion models, what we do is that we first specify a destruction process, and destruction process is generally pre-specified. It's fixed. There's nothing to learn here. And the way this destruction process works is that we take an image and we add small amounts of Gaussian noise to it every step. So you can see that I start with this clean image. Every step I'm adding a little bit of noise. And if I keep doing this for enough number of times, I'll end up with an image that is indistinguishable from Gaussian noise, right? And this destructive process is very easy to come. We can create arbitrary kinds of destructive processes like this. And what we are actually interested in is training a model that can reverse this destruction process. So the logic behind it is that if we can learn how to reverse this destruction process, then we can start from a Gaussian noise, and we can start and we can get a new sample from the data distribution. So that would be pretty amazing if we are able to do that. So I'm just going to formalize what I talked about right now. So we basically define like a Markov chain graphical model that goes from this x0 to x1 to x2 up to xt, where x0 is the left image and xt is the right image. And the following three things hold in this Markov chain. So the q of x naught is the data distribution. So the distribution of these images is the same as the data distribution. And at every step, the transition function is basically adding small amount of Gaussian noise to the image before. So it's a Markov chain because it's not depending on all the images before it, only the penultimate image. And we run it such that the final distribution q of xt is approximately equal to standard normal Gaussian distribution. Now, one interesting property, and the reason why we parameterize it like this, so we could have parameterized the destructive process by like blurring the image so that eventually we get like a white image or something like that. So you can construct many different kinds of destructive processes like it, and people have tried to do that. But one beautiful property of defining it like this, where we are adding Gaussian noise, is that first of all, you can in a closed form construct this distribution, which allows us to go to an arbitrary image at any time step t from the original image. So we don't actually have to run this forward process ourselves iteratively to obtain like a noisy image at any time step t. It can actually be represented in this closed form Gaussian distribution. So it's also, again, a Gaussian distribution, and we have easy access to this, which proves very, very helpful when we start training these models.
Sorry, how much? So beta t is what? Some number
So beta
between.
t is like a hyperparameter that we define before training the diffusion model. And there are certain properties of beta t that I'll talk about later as well. And so this is basically the parameter that we will need to define, the beta t's for every time step. And then alpha t is basically derived from beta t.
And how? What are typical values of t that you end up needing?
So generally, I think in the original paper, they started from 0 to 1,000. So they set x0 and capital T was 1,000. So it's like a 1,000-step destruction process.
I see. The only reason I'm asking is that because in the formula that you have on the next page, right? You're basically multiplying, numbers smaller than one. So could it have any numerical issues and so on?
Right. That's actually a good question. And I think initially when we implemented these things, we were using float 64 precision for this kind of calculation. Yes. And that was actually necessary because these get very, very small eventually. And we actually want them to get small, by the way. And also one thing that I can emphasize here is that these beta t's are generally very small compared to x. So that, and what we're basically doing here is that scaling down x a little bit and adding a little bit noise. So in this entire process, the variance of the data remains the same. If we assume that the initial xt has the same variance as standard normal Gaussian distribution. So we are not blowing up the variance as we keep adding more and more noise to this data because we are scaling the data down a little bit every noising step. And these beta t's are these beta t's are extremely small compared to this xt. And you can imagine that the smaller the beta t are, the more steps you have to take for noising to actually arrive at the standard Gaussian normal distribution. So this is the trade-off that you have to decide on when training these diffusion models. Okay, so just summarizing the forward. Sorry, go ahead.
I was just going to ask, is there a relation between beta t and beta t plus 1 or?
So generally, this is the noise schedule basically that we define. So I'll talk about it later, like how do we define this? This is basically like a function with respect to t, right, that you have to define. So just to summarize again, this is the forward process. You basically get a data, you add noise, and finally you end up with this. And you keep repeating this process again and again, the middle one. And let's define a reverse process. So reverse process would be something where initially we start from standard normal distribution. We somehow magically learn to reverse this corruption process one at a time. We keep running it, and eventually the x zeros that we will end up with, which should resemble the data distribution. So this is the quantity that we don't know in this reverse process, and we would like to learn that. I guess here having theta really doesn't, it's not important because this is like known to us, and this is the final result that we care about. So this is the theta that we need to learn. How do we reverse this forward process? Okay, so if we set beta t to be significantly smaller compared to the variance of xt, which is something that we do for diffusion models, the functional form of this reverse distribution is the same as the forward process. So the forward process we defined was a standard normal Gaussian distribution, this particular distribution in the middle that I'm talking about. And if the beta t's are sufficiently small, we can approximate this reverse distribution to be of the same functional form, that is a unimodal Gaussian distribution. And I guess the intuition here is that if you imagine beta t to be 0, then this holds, right? Because it's basically an identity function, so it's the same distribution. And if the beta t's are small enough, then this can be, you can imagine that denoising from removing a very small amount of noise is still a unimodal problem because you haven't really destroyed any modes in the data by adding a little bit amount of noise to the image. So given that our forward process was a set of Gaussian distributions, we can parameterize our reverse process also as a Gaussian distribution. So now it basically becomes a matter of learning this mean and this variance given the noisy image xt and a time step t. And once we have this, we can sample xt plus 1. I think actually, sorry, this would be xt plus 1 here, sorry. And so given the xt plus 1, we can then sample xt from it and just keep reversing the process. One more thing that we generally do is that we don't learn this variance. We can compute what the variance should be in closed form, so we don't need to learn it. We can see that later how we can compute it in closed form, and we only learn the mean. And okay, so now we have determined what p theta should look like. And now we will basically try to optimize the maximum likelihood. And the way we will optimize the maximum likelihood is sample a data point from the data distribution and compute the log likelihood under this probability distribution that we created, which can be broken down into these transition probabilities. And if we can compute this in closed form, if we can get a nice objective function out of it, we can just optimize theta to just maximize this, and we would end up learning these transition functions. There's a lot of simplification that happens in this optimization, like in figuring out, in basically optimizing this objective function. I wouldn't go through all those simplifications here. It's like a long proof that you guys can look at in this, I guess, in the original DDPM paper. But what happens is that, first of all, we cannot estimate the likelihood exactly. So we'll have to approximate the lower bound on the maximum likelihood estimation. And this is what that lower bound looks like. And generally, this is the case with a lot of maximum likelihood models where we're not able to estimate it exactly. So we try to optimize the lower bound. And maximizing the lower bound is fine, because if you maximize the lower bound, you're also maximizing the original function. And here we can ignore some parts of it for now because it's not really relevant here. So first of all, this part on the left, the L capital T, is basically a constant because we already know P of xt, so there's nothing to learn here. And the right part is also something that we can ignore for now in the interest of time, and we just care about this LT minus 1. So this LT minus 1 is basically a KL divergence between this probability distribution, which is actually, so we know what Q of xt given xt minus 1 is, and we can compute this particular distribution as well from that. And this is the distribution on the right that we care about. So we need to minimize the KL divergence between them. And again, just because of the way we formulated the destruction process, this distribution on the left side also turns out to be a unimodal Gaussian distribution. And this is the functional form of that. It's a little bit complex, but it's easily derivable from the forward process formulation. And yeah, as you can see, the variance is actually pre-specified. So if we have constructed the forward process ourselves, we don't really need to learn this thing. We can just like plug it in the reverse process to approximate this distribution. And given that both of these are like unimodal Gaussian distributions, the KL divergence basically becomes a function of like matching the mean of the left and right distributions, because we know the variance already. So yeah, so again, so this is the mean that we have from the left side, and this is the mean that we talked about, the way we would parameterize the model. Again, this would be xt plus 1, by the way. But yeah, I think it actually follows well here, because here we are xt minus 1, so this should be xt. And we basically need to learn this mapping. And again, recall that given that we were talking about this transition function of q of xt given x0, which was a Gaussian distribution, so xt is basically can be written in this form, where we again have epsilon, which is a standard normal Gaussian sample, and we have x0, and we just scale it down, add this noise to it, and obtain xt. So this is the input to the model. And also the input to the model is this t. So in a way, the model already knows what xt is. The model already knows what alpha t is. The model knows model already knows all these things. The only thing that the model doesn't know is what is x0 here, right? So this part of the target can actually be approximated by the model completely because it has all this information, the right part of it, and the left part in the target, we just don't know what x0 is. So essentially, if you look again, it again becomes like a denoising problem, right? Because we have this noisy image. We know something about how much noise was added because we know what time step we are at, and we just need to approximate how much noise was added. And then once we have that, we can just denoise the image. And after again some more simplifications to this LT minus 1 objective, we end up with this this objective function where we have this objective function gives us some weighting for each different noise level. So this is a so there should also be an expectation over t here. So we sample t uniformly, and then this is the weight that each t gets, and yeah, this is basically essentially a denoising network that we are training here. Okay, and one thing that the original DDPM paper said was that we can also remove this weighting and basically just drop it and just call this L simple, which is a weighted version of the original elbow objective. So note that once we drop it, it's not optimizing maximum likelihood or lower bound of maximum likelihood anymore. It's just a different objective function, but it can just be considered as a weighted version of the original objective function. And we call it L simple because it indeed looks simpler, because there's just not the weight like this. This weight just doesn't exist in this. And now I'm going to put back our original score matching objective function here. And you can now see the similarity between them. It's basically the same thing that we are trying to learn in both of these things, where in the first case, we also have some scaling of x. In the score matching, we did not have any scaling of x. And that's why like these two things are, so the second one is called like variance exploding process, and the first one is called variance preserving process for this reason. But yeah, the main point is that we arrived at these two objective functions with a very different design choice. In first time, we were trying to optimize for score matching. In the second time, we were just optimizing for maximum likelihood, and we just dropped some weights in there, weights from there, and then we just end up with the same objective function. And this relationship has been explored a lot more in the recent works. So one paper that I pointed out here talks about what kind of weightings exist here under which these two objective functions under which score matching objective basically becomes equivalent to the elbow objective function. And this is like a very active area of research. Yeah, another paper I would highly recommend reading is this work, which formalizes the connection between diffusion models and score-based generative models. And also, so far, we've been talking about very discrete steps, right? So our sigma i's were discrete, our time steps were discrete, but there's no reason for this entire thing to be discrete. So they formulate this entire thing as a SDE, and the sampling can also be just considered as a continuous process, and anything that we do is basically like a discrete approximation to that. So this very cleanly summarizes the relation between these two classes of models as well. Okay, so there's a lot of math here. I don't think we have too much math after this. Maybe a little bit more. But yeah, so the objective function for training diffusion models, the training step basically becomes, okay, I'm going to sample a data point. I'm going to sample a t uniformly from 1 to capital T, which is equivalent to sampling a sigma, like we were doing in score matching. Again, I'm going to sample an epsilon, which is a standard normal Gaussian distribution sample, and I'm just training a model to denoise the image. And sampling works in a similar way. Sampling basically comes down to this objective function. And again, you can see a very clear similarity with the Langevin dynamics sampler, where we have the z, and this epsilon theta is basically the score. So which is basically what the Langevin dynamics had. So if you consider these, like if you just remove these constants here, it basically becomes like a very equivalent sampling function eventually.
And remind me what alpha bar is?
Oh yeah, so the alpha bar was basically defined as
some accumulated.
Yeah, some cumulative product of these betas. So these 1 minus betas would be very close to 1 because these betas are very small. But if you multiply them enough, then the alpha t's would become 0 eventually. So at capital T, this alpha t would be so small that x0 would be completely destroyed.
I had a question.
Yeah.
So I see that like in the objectives, like each like I guess each time step, or like like intermediate distribution, like is weighted equally. But to me, it feels like the early denoising process is like more difficult, right? So
Yeah, that's a very good question. But it's actually not weighted equally here. And the reason is that we haven't yet talked about what these alpha t's are as a function of t. So I could design an alpha t schedule where even at the earliest time step, I'm already adding a lot of noise, right?
or at least in the score framework,
Oh, in the score one, right? Okay, so in the score one, let's just go back to that. Yeah. So in the score one, you're saying that we are sampling one of these noises and doing this. So I think they talk about, I think you can do anything here in the second step. You can decide what is the distribution through which you want to sample these sigma i's, I guess. So that would be one way to control different noise levels. But as you were saying, I think this is actually something I will talk about later on. But this is one of the things that is very important to tune for these diffusion models, because different noise levels, there is a different level of difficulty of denoising. So you want to spend most of your model capacity on denoising where it actually matters.
Yeah, that makes sense.
Okay, so just again, I would, on the right side, I have this here just to emphasize again and again what's happening here. So every sampling step, we have some XT available to us. And our model is basically predicting the noise that was added to XT if we would have gotten to XT from a forward pass. And once we have that, we can estimate XT minus 1 from it. And from score conditioning, we also learned that this predicted noise is essentially the score of the true data distribution. So, so essentially, what we are doing is taking steps in that direction. So this noise is actually pointing in opposite direction of the score, which you would probably have seen when I reparameterize the score function to absorb the negative sign. But yeah, this is basically essentially what we're doing here. Every step we are denoising, and this noise that we get from this denoising process is actually the negative direction of the score. So we just make progress in that score direction. Okay, this is a visualization I love from one of the blog posts from Sander Tillman. So I'm just going to describe this sampling process again through this diagram. So, okay, so at any point we are at XT, and this is the sample that we are trying to reach, right? So at this point, we are going to denoise it, and denoising will give us a direction to go for this sample. Now, this direction wouldn't be perfect right away because it's just a one-step prediction, and this gradient is basically pointing in this direction, and this is the this is the x0 we would get if we remove the predicted noise from this image, which is very blurry right now. You can see. So you can imagine that this is a distribution. In the center, it's like blurry images, and on the peripheries are the actual manifold of the data distribution that we care about. So this is the gradient that we got. We are not going to go all the way here because remember, we take very small steps in this direction. And this is the small step that we take. And then we have the Z component, which was a noise that we add to the sampling process every step, which then allows us to introduce some randomness to this process. So let's say we have so many different options. We choose one of these epsilons, and now we end up with this is the XT minus 1 after applying the full update. Now we repeat this process again. We again get a new x0. We take a gradient, we predict the noise, we take a direction in that, we end up with xt minus 2. And yeah, if you keep doing that, and you will arrive at x theta, or x naught eventually. This is also like one video that I had created at some point. Here, ignore the left side because there is a conditioning here, is a super resolution, but this is what the image generation would look like on the right side, generally. So yeah, you can see that we start with pure noise, and here the denoising process is actually denoising process conditioned on the flow resolution. That's why you're seeing so much similarity here, but it kind of tells you how the denoising process happens. Okay. Yeah. Any questions at this point? Okay. So this is again just rewriting the sampling process that we had. I've just replaced these constants with AT, BT, and CD just to make it simple. And again, when I replace this epsilon with the score, I just change this constant here. And yeah, I just wanted to emphasize that thing again, that it's basically every step we are taking in a small step in the direction of high probability region. And if we run the sampling step several times, we end up with a sample that has a high log likelihood under the distribution. Now let's talk about conditional diffusion models, because generating images by themselves is not as interesting. You do need some kind of control so that you can actually do something productive with these generative models. And what are the kind of controls that we can think of? So for example, if you're trying to train a super resolution model, we will have a low resolution image as input. If we are thinking of a text to image model, we will have the text as input. If we are thinking of a colorization model, we'll have a black and white image as input. And from a modeling perspective, we had this denoiser. Now this denoiser has this extra conditioning signal, and we can provide it however way we want it. And we don't even do anything. We just provide this conditioning signal to the model, and this conditioning signal, you can think of it this way, that this is a denoiser, right? It takes a noisy image and removes noise from it. So any conditioning signal that can automatically help the model to denoise better, it will just use it. You don't need to enforce that conditioning signal anyhow. You just pass that conditioning signal, create an architecture in such a way that it's easy for the model to take information from it, and it will automatically take it if there is something to learn from that condition signal. Again, if we just look at this sampling function, the way we just replace it is that we just have this condition signal now, and instead of the score of the xt, now we have the score of the xt given c. So we are taking steps in the direction where the probability of an image given this conditioning signal is higher, not just any image. So in practice, this doesn't work. When you start sampling like this, you would end up with an image. So this is something that is very interesting in text to image. So if I just take a text to image model and run sampling like this, it just doesn't work. It will, if I say horse riding an astronaut, it will give me like some image which looks like a horse riding astronaut, but it's not aligned at all. And one of the things that you need to do to actually make it work is classifier guidance, which I'm going to talk about now. Okay, so the fact that this is actually essentially like a gradient ascent algorithm where we are taking steps in the direction of high log likelihood of xt given c. Let's say we also have an access to a classifier. And what this classifier tells us is that given a noisy image, it tells us the probability of a class. So for now, let's imagine that we have a classifier that can classify between a cat image and a dog image. And our conditioning signal is like a cat. And we have a classifier that can take a noisy image and give us a probability of a cat, of that image being of a cat versus a dog. Now, during sampling, we can inject this particular quantity here, which is again like the score function of the classifier with respect to xt. So what we are basically telling the sampler is that at every step, not only go to a region with high probability of xt under c, but also go to the region where if we pass that image to the classifier, it is very sure that it is actually that conditioning signal, that it is actually that class. So for example, in case of cat, we want to go to a region of xt where if we pass that to the classifier would give higher and higher probability that it is indeed a cat. And this lambda weight here that we apply to this particular quantity here can be thought of as augmenting the classifier to like this distribution where we even accentuate these classifier probabilities. So you can imagine the classifier is like giving a simplex output. So every value, it just sums up to 1. And the higher the value of lambda is, anything, the maximum of that classifier, wherever the maximum logic is, will be the only one that's remaining, and everything else is 0 out. So the higher the value of lambda, the more we want to focus on the mode of the classifier. So we are basically saying that don't give even 0.01 probability to a dog. I want exactly 1 probability to the cat if I run it through my classifier. Does that make sense? This is like one of the most crucial concept of like making diffusion models work for conditioning signals.
And you're saying that this is essential, right? Or is it just like a...
So this is essential for text to image generation. So when you have conditioning signals that are simpler. So for example, super resolution, where there is so text is a much weaker conditioning signal than like a low resolution image. And we find that in any kind of those conditioning signals where you have a strong conditioning signal, it kind of works fine. You don't need guidance. But whenever you end up with a weaker conditioning signal like text, there you definitely need guidance to make it work at all.
But here it's not dog versus cat, right? Like the space is huge, that it can be any text prompt.
I'm going to talk about that as well. So for the here for the simplicity, I just called it a classifier, but it can be actually something that gives you a probability of a conditioning signal given xt. So yeah, again, just following up on that example. So a dog versus a cat, and we are basically saying that guide us towards images where p of cat given xt is. So if you're generating a sample of dog, we are just saying that guide us towards images where p of cat given xt is 0. It's basically close to 0. The higher the lambda, the more we emphasize on this thing. So now imagine what the diffusion model would do. So it will generate images where the dog is facing towards the camera front and center. Because anything slightly deviating from that, classifier may say that it's 0.99 dog and like 0.01 cat because it's not really sure, you know? So for example, if you see the images on the right, if the dog is sideways, maybe the classifier is a little bit unsure about dog versus cat. If there is also a dog and a cat in the image, there will be like 0.5 probability. So the model will never generate images like this if you start using guidance. It will always generate an image where the dog is at the front and center, and it's very clear that it's a dog and there's nothing else in the image. So if you had a classifier where there was dog, cat, and grass, let's say 3 classes, then it would never generate an image where a dog is on the grass, because then the classifier will have some probability for grass as well. And this is one of the reasons why the more guidance you apply, the better samples you get, but the diversity gets compromised because you just cannot generate interesting samples anymore. They all would look like very sharp, very like, they all will have this structure where the main object is at front and center and everything else is like blurred out or whatever. Okay, so what does this classifier look like? So for example, if you're training a class conditional ImageNet model, then this classifier would take a noisy image and predict one of the 1,000 ImageNet classes, right? So we actually need to train a classifier because it's not a typical classifier. It also has to take a noisy image as input. So you can see here that it actually takes xt as input, and typical classifiers take only like the noiseless images as input. So you actually have to train the classifier for this thing. And for text to image, this can be like an autoregressive captioner. So it takes a noisy image, it takes the caption, and then it outputs the log likelihood of that caption, basically. But the disadvantage, of course, here is that we need to train a classifier for every new task. So now we need to train a captioner if we want to train a text-to-image model, which is not really ideal. And the objective that we are training the captioner on is very different than the objective that we're using it for. So this was an idea that came around, but just quickly like faded away because it was just impractical. And it got substituted with this much cooler way of doing things, which is classifier-free guidance. So as the name suggests, you just don't want classifier anymore, but you want the same effect. And it's actually very, very simple and elegant. So this was the gradient that we cared about, right? And we can actually just like write base rule here. And you can see that this basically simplifies to having access to the gradient of xt given c that we already have. This is the diffusion model that we already trained. And this new gradient, which is basically the unconditional distribution score. So the way we can do it is that whenever we train a diffusion model condition on something, some percentage of time, typically 10-20% of time, we can just drop that conditioning signal during training. And that just lets the model learn this unconditional distribution as well. So it just becomes drastically simpler where we are just training a model and we just drop conditioning signals sometimes, and during sampling, we don't have to do anything anymore. So yeah, this was the...
How are we getting this P of xt given C?
Oh, so this is the original diffusion model that we trained, right? So we pass the conditioning signal here, right? So this E epsilon theta of, this is the network that we trained, right? Where we pass the conditioning signal. And this is the score function that we were learning, which is xt given C, whenever we have some conditioning signal for diffusion models.
Right.
And this is what we needed, right? So we needed like a P of C given xt for the classifier, which we didn't have access
Right.
to. That's why we need to train a classifier. And now we are basically showing that this can be approximated using the original score that we had and also an unconditional diffusion model score. And yeah, it's very simple to estimate it because we can just drop the conditioning signal sometimes during training. So just like putting it back together, the equation here was the one that we started out with, where we needed xt given c and we c given xt. And now we just replace c given xt with the equation above, and we just end up getting this equation where now this lambda is being applied on both sides just because of how it turns out to be. And we can easily calculate both of these quantities using the same diffusion model that we have. So also one thing to note here is that now every sampling step, we have to run the diffusion model twice, once with the conditioning signal and once with zeroing out the conditioning signal. And this is one of the pain points with diffusion models that you have to, even if you're running 100 steps of sampling, it's actually 200 model function calls now because every step is 2 function calls.
Isn't this parallelizable in some way? Like
this is parallelizable, yeah. So you can compute these two. So like flop-wise, it's just 2x the flops, basically.
But
you
like, can't you just design an architecture where like things can be
Yeah, so I
shared?
guess
Maybe not.
yeah, you can do that, but it generally turns out to be worse. One thing that people do is that they actually train a weaker model for the right term. So they train a separate model that is just much smaller, and they say that it's actually better to train a much smaller model, because essentially what this equation is telling you is that guide towards the conditioning signal and guide away from all other images, right? So it's saying that there is a score for images in general, and there is a score for images conditioned on this conditioning signal. Guide towards one and against the other, right? And what people have now done is to generalize this, where they say that I don't want to guide against all images, I want to guide against specifically bad images. And they train this model on the right on only bad images, and that leads to better fidelity of overall generation. So there are like a lot of tricks that people have done to like, and there's no like clear mathematical reasoning behind it, but this process of like training separate models for these two things and using different distributions for them like works very, very well in modern diffusion models. Okay, so one more thing I want to talk about is a challenge that we face with diffusion models. So again, just to emphasize, this is the epsilon theta that we substitute at every step, which is essentially this epsilon noise that we somehow estimated. So technically at each sampling step, we can reconstruct the x0 hat from all the input that we have. So we have access to xt, we have access to the predicted noise, so we can compute the x0 hat. And this should simulate the fully denoised image that we currently have approximated. So again, just going back to the original visualization, these are the x0, the blurry image x0s that I'm talking about. So this is something that we can obtain at every sampling step. And we can do a lot of fun operations to it. So first of all, one thing to note is that our original x0 data had a predefined range. So for example, when it comes to images, they generally have a range of -1 to 1 or like 0 to 1 or whatever. And we also don't want our intermediate x0 predictions, the x0 hats, to deviate from this range, because then we might just go into a trajectory where we are not familiar with. And you could impose that using some architecture constraints in the diffusion model, so apply some like sigmoid or like tan h at the end. But we generally don't do that because it generally doesn't work and makes the architecture more unstable. But what we can do is that we can extract this x0 hat every sampling step, do some operations to it. So for example, clip the values between -1 to 1, or like do some fancy operations to it, and then recalculate this EPS, and then plug it in the sampling and continue our sampling. So you can always at every step just extract back the x0 hat, make it satisfy certain properties that you care about, and then compute the epsilon back and plug it in and keep sampling. So this iterative sampling process gives you a lot of such freedom to play around with the model. So for example, if you want to generate symmetric images, right? One thing you could do is that you could take out this x0 hat at every sampling step and just make the left side the same as the right side, just force it, right? And you just plug in the epsilon back, and what you will find is that the final image generated is actually like a symmetric image. So you can do all these like tricks around, or maybe you can make the border of the image white, and you can just force the fact that the images have a white border in them or something like that. So this thresholding thing is something, so this fact that the images are supposed to have predefined range and this X0 can completely deviate from it because there's no architecture level constraint on it is actually like a very big problem. And the problem happens more when you have high guidance weight. So if these lambdas are very high, it typically turns out to be like a very big problem. And here I'm showing some samples that we had originally from the text to image model. So on the left side, you can see that we are doing no thresholding. And each row is a different guidance weight. So the first row is guidance weight of 1. Guidance weight of 1 basically means no guidance in classifier free guidance. If you plug 1 here, then this zeroes out. The second row is guidance weight 2, and so on and so forth, up until guidance weight of 5. So on the left side, with no thresholding, where we don't touch X0 at all, you can see that we start generating completely black images because we completely go beyond the range, and then the model never corrects itself. On the left, on the second and the third column, you can see that we apply some kind of operations on this X0, and we are able to recover much better images out of it. And the method that we proposed at that point was dynamic thresholding. I wouldn't describe the process here, but it just applies some tricks on top of the images to make it look more, to make the images have a better dynamic range, because that gives like better quality images. And I guess you can also see here, by the way, that guidance weight 1 just gives you really bad samples. So you can see that it kind of looks like an astronaut riding the horse, but it doesn't make sense at all. Whereas guidance weight 5 just looks like such a better sample here.
By the way, Chitwan, we are a bit ahead of time, so.
Oh, okay. So yeah, I just have
So
like a few more slides. Yeah.
Okay.
Okay. So I have like 7 minutes right now, right? 6-7 minutes?
No, actually, like it's 3:45.
Oh, okay. Sorry. Okay, I completely
Yeah,
forgot. Okay.
I'm sorry.
Yeah, it's fine. But I'll just like give you like a very quick
Yes.
slides on. So this is just like some slides on using diffusion models in practice. So let's say we want to generate a 1K by 1K image, which is still a very high resolution that we need to model. So one thing that we still do is compress these images into low dimensional latent space, like the diagram below. And if you remember, I talked about this as a demerit of autoregressive model, but one of the issues with autoregressive models was that we had to map it to discrete tokens in the latent space. But here we don't need to do that. We can map it to continuous tokens, and the compression ratio is much less because of that. So these autoencoders are much better at reconstructing images, and it helps us to just lower the dimensionality on which we model images. And so this is one way of modeling high resolution images: compress them, model them in the low resolution latent space, and then generate a sample and then decode it back. Another approach that we explored at some point was this cascaded generation, where you first run diffusion model to generate a 32 by 32 image, then take that 32 by 32 image and train another diffusion model to upsample it, and just keep doing it till you get like the resolution of your choice. And here, what you can do is that throw a lot of compute at the lower resolution, because a lot of things are being decided there. And then in the higher resolution, you can just throw less and less compute, so that even when the resolutions get higher, you don't need to use a lot of compute there, because the task keeps getting easier and easier. The architecture-wise, there are two main architectures that we use for diffusion models. There's a unit architecture, and then there is a diffusion transformer architecture. Right, and most of the time now, I think most people use diffusion transformer, which is basically just taking these latents and just feeding them as tokens, like patching with some patching to the transformer, and just running the transformer and getting the output. So only one requirement for the architecture of a diffusion model, and that is that the input and output dimension should be the same. The reason for this is that we are actually predicting the score, and score needs to have the same dimension as the input with respect to which the score is being computed. And no other requirement at all, no causal masking, nothing else. So that is one of the beauties of these models. Another thing that I alluded to initially was noise schedule. So as you can see here in training, we are sampling this time step uniformly and then selecting alpha t based on that. So this can be characterized as a noise schedule function that we need to specify before training the model. And generally, the way we describe it is a log SNR function, which is basically defined as this. And it's basically signal to noise. So alpha t bar is the signal, and And 1 minus infinity bar is the variance, so the noise. So the higher the log SNR, the less noise you're adding, and the lower the log SNR, the more noise you're adding. Yeah, these are like examples of the noise schedules that we use for training. So you can see most of the noise schedules here, especially the blue one, which is the most common noise schedule that is being used. You can see that most of the time between 0.2 to 0.8 is being spent on something in between, whereas we spend very little time on very high and very low log SNR values, which kind of makes sense because denoising is impossible at very high log SNR because there's just actually denoising is, you can say denoising is very easy at very high log SNR and impossible at very low log SNR. So it doesn't make sense to spend too much time there, and we can just spend time in the middle. And also we can use a different schedule for training and sampling. So this is also something that diffusion models are known for. Like you can just, it just becomes like a completely different thing. You train a model with different noise schedule, and then you can decide what to do during sampling based on what you care about.
And it generalizes?
It generalizes. So I have skipped some details here, but you generally train it in a complete continuous form. So you do not sample like t from 1 to t. You actually sample t from 0 to 1 uniformly.
Okay.
And there are like certain generalizations that people have done so that it becomes like a completely continuous domain problem instead of sampling these discrete time steps. Yeah, and another thing that I alluded to initially was that diffusion models are very slow to sample. So typically they require 100 to 1,000 sampling iterations to converge to a sample. If you compare this with GANs, VAEs, and normalizing flows, they require exactly 1 forward pass to compute the sample. So diffusion models better be very, very good to require these many sampling steps. And they are, and that's why people still keep using it. And there are many papers that have talked about how to make it faster without retraining it. So let's say I have access to the diffusion model and I just care about how to make it faster. These papers are like sample time changes to make the model faster. So they basically figure out different ways of approximating the trajectories, make the sampling trajectory smoother so you can take like larger steps and so on and so forth. One approach that is also that does require you to train a new model is distillation. So what you effectively do is that you have a teacher model that has been trained that requires 100 steps of sampling. Now you train a student model to approximate the 2-step denoising of the teacher into 1-step denoising. And you keep doing this, and every time you do this, you drop your sampling steps by a half. So if you do it like a couple of times, you end up with a teacher that actually can generate samples in like 3 steps or 4 steps or something like that. And it has been very promising actually, and something that a lot of people in the literature do now. Yeah, and I've just attached like more references here. These are some of the papers that I think if you go through them, they would give you a very, very good idea of what people care about in the modern diffusion models, what matters, what doesn't matter. So yeah, I would just recommend you to read some of these papers. And yeah, that's pretty much it from my end. Yeah, if you have any more questions right now, I can just take it. But yeah, that's pretty much it from my end.
Okay, any questions? Okay, well, thank you so much, Chitwan. This is like a fascinating area. We haven't talked that much in class about it so far, but my interest already is peaked in kind of different directions in this area. So thank you so much. Your talk was so interesting. We went 15 minutes over, but I think it's fine. So thank you so much. And just to the rest, we will meet next on Monday. Huh?
Thank you.
Thanks, Chitwan.
Bye.